We know that, according to Bohr's atomic model, electrons in an atom revolve around the nucleus in circular orbits. The nucleus contains protons and neutrons. Protons are positively charged particles, whereas neutrons do not carry any charge. That is, they are electrically neutral. Thus, the net charge of the nucleus is positive. Electrons revolve around the nucleus in circular orbits due to the electrostatic force between the electrons in the orbits and the protons in the nucleus. Consider an electron with a charge -e revolving around the nucleus in an orbit of radius r. The charge of the nucleus is Ze, where Z is the atomic number of the element under consideration. Current due to the revolving electron I is equal to E by T, where T is the time taken by the electron to complete one revolution, called the time period of revolution. Let this be equation 1. When the electron revolves in the orbit of radius r with a constant speed v, then the time period of revolution t is equal to the circumference of the orbit by the speed of the electron v. The circumference of the orbit of radius r is equal to 2 pi r. Hence, t is equal to 2 pi r by v. Let this be equation 2. Substitute equation 2 in equation 1 to arrive at the relation I is equal to EV by 2 pi r. Let this be equation 3. We know that the magnitude of the magnetic moment M of a current-carrying loop is equal to the product of the current and the area of the loop. That is, M is equal to IA. At the atomic level, electrons or any charged particles moving in uniform circular paths have a magnetic dipole moment which is called the orbital magnetic moment. It is denoted by the Greek letter μL. The subscript L in μL indicates that the magnetic moment is of an orbital nature. Thus, the magnetic moment of the orbiting electron, μL, is equal to the product of the current I and the area of the orbit A. Let this be equation 4. The area of the orbit A is equal to pi r square. Let this be equation 5. Substituting equations 3 and 5 in equation 4 and simplifying, we get the expression for the magnetic moment of the revolving electron as μL is equal to EVR by 2. Let this be equation 6. Multiply the numerator and the denominator of equation 6 with the mass of the electron, ME. Rearranging the terms of equation 6 as shown, we get equation 7. The electron is in circular motion around the nucleus. We know that the magnitude of the angular momentum of the electron around the nucleus is given by L is equal to MEVR. Let this be equation 8. Substituting equation 8 in equation 7 and simplifying, we get the equation μL is equal to E by 2 ME into L. Let this be equation 9. In general, the magnetic moment associated with any charged particle having charge Q, mass m, and moving in uniform circular motion is called orbital magnetic moment. It is given by the expression μL is equal to Q by 2m into L, where L is the angular momentum of the charged particle. We know that the direction of the conventional current is opposite to the direction of the motion of electrons. In general, we refer to this conventional current as the electric current. Now, by using the right-hand thumb rule, we can find the direction of the magnetic momentum of the electrons. Curl the fingers of your stretched right hand along the direction of the current. The thumb then indicates the direction of the magnetic momentum. On the other hand, if we need to find the direction of the angular momentum of the electron, we use the right-hand rule again. In this case, we curl the fingers of the stretched right hand along the direction of velocity of the electron. Then, the thumb indicates the direction of the angular momentum. Thus, we find that the angular momentum of the electron and its magnetic momentum are in opposite directions. Vectorially, the relation between the magnetic momentum and angular momentum of an electron is mu L is equal to minus E by 2 me into L. The negative sign indicates that mu L and L are in opposite directions. Now, let us discuss about Bohr's magneton. According to Bohr's atomic model, angular momentum of an electron revolving in an atomic orbit is quantized. That is, the angular momentum L is integral multiples of h by 2 pi. Hence, we get the equation L is equal to n into h by 2 pi, where h is the Planck's constant, whose value is 6.626 into 10 power minus 34 joules second. Let this be equation 10. Here, n can take the values 1, 2, 3, and so on. Substituting equation 10 in equation 9 and simplifying, we get the magnetic moment mu L is equal to NEH by 4 pi me. Let this be equation 11. For an electron, the magnetic moment is minimum for n equal to 1. By substituting all the standard values of the constants in the equation and simplifying, we get the magnetic moment as 9.27 into 10 power minus 24 ampere meter square. This value is called Bohr magneton. This is also referred to as the spin magnetic moment. Now let us discuss about the gyromagnetic ratio. The ratio of the magnetic moment to the angular moment is called the gyromagnetic ratio. It is denoted by gamma. That is, gamma is equal to mu L by L. On substituting the value of mu L from equation 9 and simplifying, we get gamma is equal to E by 2 me. On substituting the values of charge and mass of the electron and simplifying, we get the gyromagnetic ratio of an electron as 8.8 into 10 power 10 coulomb per kilogram.